Welcome back, folks. I wanted you to feel at home, so there's not too many good pictures of Copernicus Hall, but there you go. Uh, uh, I traded that basement for this basement. So let's do another video. Okay, mesh shortcut. You can absolutely do it on this type of problem. It is way more difficult. It's way more error prone. And that's when I stop myself. And because I want to get to the right answer and I want to get to it consistently. Quick is good. Quick is really useful, and we're going to use it in our subsequent lectures this semester. But it's got to be right. And when this type of problem comes up, maybe you've guessed already what kind of problem it is. When this type of problem comes up, I don't feel confident enough to do it myself, and I really kind of don't recommend that you do. If you want to try it, go for it, but you got to make sure you get the right answer. Okay, so there it is. Anybody notice what's different about it? Let's see. All that looks the same, but we've got this diamond over here. We've got a dependent a dependent supply, period. That's what's going to make me take pause. I'm looking at that one, and I think it's a dependent voltage supply. Now, just because I'm not going to do the full-out shortcut on this doesn't mean that it's not useful for part of the problem. Okay, so let's see. Two mesh currents. So I have two unknowns. All right. So we'll set up our system to look like this. And we're going to, do we have any current supplies? I don't see a single current supply, so we're going to write two KVLs, a KVL for I1 and a KVL for I2. Now the KVL for I1 is going to be like all of the other ones we've done before, and that's where the shortcut is still useful. I can get at least half of this problem done using the shortcut, so maybe I can save some time with it. But we got to know when to use it and when not to use it. There's no dependent supply that comes into play as I write that KVL. So I'm comfortable using the shortcut. What does I1 touch? 6, the 2, and the 4. So add those up and it's 12. And it's a positive because we're writing the KVL for I1, and that's what I1 touches. What does I1 share with I2? It just shares this 4. So it's going to be negative 4. And then does it go up or down across the 12 volt? Okay, so following it clockwise, we're going from positive to negative. So it's going to be negative 12 on the right hand side. All right, when I get the old system from the previous video and I plop it down here, you're going to find that that is identical other than the signs, but all of the signs are different, so we're safe. The one that's a little uglier is this one, because how do I deal with this? How do I deal with this? And there's some clever ways. I've seen people add the control variable as another unknown and then deal with it in that respect, which I think is pretty cool. But I think it's pretty error prone. So what I'm suggesting to you here is stop and write it the old way. Okay, so write the KVL for I2. I'm going to go up across 12. I'm going to go down across 4, I2 minus I1. I'm going to go down across the 8 in front of I2. I'm going to go down across 4 in front of I2. And then I'm going to go up 3Vx. And I'm back to where I started, so that's equal to 0. It's behind my head. Okay, so that Vx is the problem, right? This Vx, once again, causing problems for us. So we got to write an expression for whatever Vx is. Where is it? It's up here. Okay, so it looks like it's 2 ohms times, well, the positive direction is going to be to the right. I1 touches that resistor and goes in the positive direction. I2 doesn't touch that resistor. So the current through it is just simply positive I2 and times R2. So we're going to kind of swap those around and say it's 2I1. I1, Dave. 1 is this many. And that's the correct subscript. That would have stunk. Okay, so do it the way we've been doing it before we introduce the shortcut. So positive 4 I1 -4, -8, and -4. So that looks like -16 I2. Double check myself quickly. And then, oh, I didn't plug in, did I? Sloppy. I'm trying to go quick. It says shortcut. I'm trying to like make that be true. That is in fact a shortcut. The first half was quick. I2. Don't forget the gain, right? 3 times 2 is 6. Plus 6 I1. Uh-oh, that changes. That changes something. Okay, so we've got +4 and we got +6, so we're going to get 10 I1. Go slow, don't screw up, be better than me, please. I'm counting on you. Someday I'm going to fly in a plane that you design. Okay, so let's see, and then we move the 12 over to the other side, so it's going to be -12. All right, sliding that up into the matrix form. That one's ready to go. It's a bunch of constants, and that's the unknown. So slide that up into here and enter it differently. So it's going to be 10 in front of I1. It's going to be -16 in front of I2. And it's going to be -12 on the right-hand side. Okay. Choose your weapon. And solve it. Okay, 12, -4, -12, 10, -16, -12. All right, and from this, I got to wrap my line. So this is just equal to all this stuff up here. It's I1, I2. And from that, we get -947.4 milliamps and 157. This one's positive 0.9 milliamps. And there's your mesh currents. Not too bad. We can still leverage using the shortcut to some extent, but we got to be careful with it. Okay, I could use it for I1. I couldn't use it for I2 because I guess you could, but because I have that voltage, that dependent voltage supply. It's important that it's dependent, and that's why. Okay, doing our check like we've been doing, because we already worked this problem before. We want to look at our previous result. Previous video, and make sure that we are consistent. And lo and behold, we are. So even cheating, not really cheating, moving fast, we get an equivalent result. So negative, oh, it's behind my head. Ready? Ooh, Ghost Dave. -947.4 milliamps, 157.9 milliamps. So those match, and we got a good result. Okay. So use the shortcut. Practice it. You're going to watch me do it. You're going to get a lot of practice doing it. It didn't come out of nowhere. It's still based on KVL, KCL, and Ohm's law. But be careful when you come to when it comes to analyzing circuits with dependent supplies. That's my only warning about it. Otherwise, we're going to have some fun with it. All right, that wraps up mesh analysis. Your first like real method of analysis. It's organized. We can use it on almost any circuit. Ooh, I said almost. We need another method of analysis. I like teaching both of these. So stay tuned, and you're going to hear about nodal analysis coming up next, and you're going to figure out what circuits you should be using nodal analysis instead of mesh analysis on. Okay? I'm excited. I hope you are too. Stay tuned and good luck.